In this video, I will show you how to do linear regression in Stata. Before you watch it, please make sure that you have watched my other two videos called Linear Regression and Linear Regression Example. I have opened up here the Stata program, and I have already executed the Stata program, and you can go to my website and download the program and the data, and you can follow along. So the first thing to do is let's take a look at the data. And this is the data that we have. We have cars, and these are the different makes, and here we have MPGs, the miles per gallon. This will be the dependent variable that we're trying to explain. And we have a weight variable, which is in pounds, or I have calculated a new variable, which is the weight in 1,000 pounds. So I just divided this one by 1,000. And then we have the price of the car, whether or not the car is foreign, and other independent variables. So in the case of the simple linear regression, this would be our dependent variable, and weight 1 would be our independent variable. And in the case of multiple regression, we would have MPG as the dependent variable and weight 1, price, and foreign as our independent variables. So this is how the program starts. We are reading the data called regression_auto, and this is the directory where I have saved the data. And we're forming global lists. For Y list, my dependent variable would be MPG. And I have X1 list, this would be the X1 variable for the simple regression, would be weight 1. And the X list for the multiple regression would be weight 1, price, and foreign. So all you have to do when you have your own data is change the name of the file that you have, change where you have saved the data file, give me the name of your dependent variable, put it right here, one dependent variable. Here you can put just one independent variable, and here you can put as many independent variables as you want to. And the rest of the program should run for you. You don't have to change anything else. And this is why I like to use these global lists, because it's very easy not to make mistakes when you're new to this. The first thing to do here is describe the data set and summarize it. And here using describe, these are the results that we have here. We have miles per gallon, car weight in 1,000 pounds, car price in $1978, and foreign is a 0-1 variable if the car is foreign or domestic. When we summarize the Y variable and the X variable, we have miles per gallon, 26 observations in the data. The mean is 20. For the weight, the mean is 3. Price, this is the mean, and foreign, 26% of the cars are foreign. We can also summarize the Y variable in detail by using summarize. Put here the name of your dependent variable, comma, detail. And here you can see the percentiles, the smallest and largest values, and the mean, standard deviation, and so on. The next thing we can do is calculate the correlation between the dependent and independent variables. And this is accomplished by using correlate, Y list, and X list. And here you have a very strong negative correlation between the dependent variable and weight, and somewhat strong but not as strong correlation between the rest of the independent variables among themselves. Next thing we can do is plot the data, and for that we will use graph two-way, and we would use the scatter plot. This is our dependent variable, and X1 would be one of our independent variables. Notice that you can't plot more than one, just you have to have one independent variable here. And if we execute this command, this is the graph that we will see. So you can see that for each X variable that we have here, this is the car weight, these are the Y variables, and we have a scatter plot. And you can see, even just looking at the graph, we're going to have a negative relationship between these two variables. And if we're to plot a regression line, it will probably come right down here somewhere. and we want to have that regression line being as close as possible to all the actual values for y. Okay, so the next thing to do is estimate the simple regression after we have plotted the data. And to accomplish this, we're using reg for regression. We're putting y list is the dependent variable and x1 list is just one of our independent variables. And this is the output that we see here once we estimate the model. The most important thing here is the coefficients that we have. And minus 5.53 is the coefficient or the slope on our independent variable weight. So the way to interpret this one is that if weight increases by 1 unit, which is measured in 1,000 pounds, then y, the dependent variable miles per gallon, would decrease by 5.53, decrease because we have a negative sign, by 5.53 units or 5.53 miles per gallon. This coefficient here is the intercept, is the constant, and this means that when x is equal to 0, which means weight is equal to 0, this is where y would hit the, this is the value of the y variable, is 38. You can also take a look at the significance of these coefficients. The standard error is provided to you. The t-statistic would be equal to the coefficient divided by the standard error. And then we want to see if these coefficients are significant, which means that these t-statistics are in the critical rejection area, typically above 2 or less than -2. And we see that this p-value is very small, it's less than 0.05, as well as this confidence interval does not contain 0 in it. These are all indications of the fact that we have significant coefficients, which means that this coefficient here is significantly different than 0, and this one is significantly different than 0. This is called an ANOVA table, and this tests for the joint significance of all coefficients. And this is the sum of squared for the model, for the residual, and the total. Degrees of freedom, we have one independent variable, 26 minus 1 observations, 26 observations minus 1 is 25. That's the degrees of freedom here. And we would have the mean squares are here, is this number divided by this, and this divided by that. And then when you divide these two numbers, you get an F statistic of 45. And we have 1 degrees of freedom in the numerator, 24 in the denominator. And the probability that the F-test statistic exceeds the critical value is less than 0.05. Therefore, we have significant results here, which means that all coefficients are jointly significantly different than 0. Another thing to look at here is the R squared, which is, R squared is calculated as this number, as the sum of squares for the model divided by the total sum of squares. So this means that we can explain 65% of the variation in the data with our model, and the rest is due to error. And the adjusted R squared just adjusts for the fact that if we have more independent variables, then it penalizes this R squared, so it is lower. The next thing that we can do here is plot the regression line. And this is accomplished by using graph two-way, scatter of y and x1. So this is exactly what we have so far here before. And in addition to that, we can put linear fit of y and x1 list. And now we can see how this thing looks like. And this is how it looks like. This is our regression line, the linear fit that we have. So these are the actual values of the variable. These are the y variables, and these are the fitted values right here. This is the regression line. So instead of just predicting this one, the predicted value would be right here on that line. This is the best that we can do. We cannot predict the error. We can just predict the y variable to be on this line. So this is what we are going to do next. We can predict the values for the dependent variable. by using predict y1 hat, that's why I call this one, comma x beta. So this is calling for the predicted values. And we can summarize y list the actual values and the predicted values. So when we summarize that, look at what we have. This is the mean for the actual variable, and y hat is our predicted values, and see how close we are. Also, if we look at the data, these are the y1 hats that we're predicting here. So notice that we have the actual value for miles per gallon being 22, and using the coefficients that we estimated, which is the intercept of 38 here, minus 5.53 times this variable, which is the x variable. This is exactly how I got that number. For the next number, y1 hat, we would use, again, 38 for the intercept, minus 5.53 times weight 1, which is our independent variable, and this is what we're going to get y1 hat for the second observation, and so on. So these y1 hats we can predict here using the command that we have here. And now that we're summarizing them, they're very close to the actual values. And now we can graph them by using the scatter diagram that we had before, and we can also scatter y1 hat and x1 list. And if I look at the graph, this is the graph that I have. So notice here that this is, for example, this is the actual value here. We can't predict it. We can predict here the fitted value for y, and the rest would be equal to an error. This is a negative error. So here we have the actual value would be here, and that would be the predicted value. Here we have a positive error in this way. So we can also plot these residuals or these errors, but instead of using this negative sloping line here, we can kind of flatten that line and just plot how these residuals differ from 0. And this is what's accomplished on the next one by using regression residuals, and we're predicting E1 hat or U1 hat, comma residuals. So you need to call the residuals here, and you can summarize these residuals. So if you look here for the summary of the residuals, we have the mean that is very close to 0. That's great because on average our residuals are not very different from 0. And you can graph this using two-way with the scatter graph. E1 had the residuals against x1, and this is the last graph that we are getting. Notice that instead of just having the downward sloping line here, we plotted everything against 0. And these are now the deviations that we have between the actual and the predicted value. The actual and the predicted value, and we have some negative errors here where the actual value is less than the predicted values. So this is how the residuals look like. And if you check the data set, we also have those calculated here. This is the E1 hat. So this E1 hat is exactly the actual value, which is 22, minus the predicted value, which is 21 point something, 0.85, and see, that's how you get the 0.14, and so on. This again is the difference between 17 and 19.53, and you can see these residuals. Some of them are like, we're actually quite off on some of the predictions. The error is quite big between the actual and predicted values, but on average we're close to 0. Okay, so this was how to do, let's see, this is how to do the residuals. The next thing that we can do is hypothesis testing to see if the coefficient is significantly different than 0. And you accomplish this by using test and putting x1 list. So you want to check if the coefficient on the x1 variable is significantly different than 0. And here we have an f-test, and you can see that this one is exactly the same as the f-test above. Okay, and again we have significance of the coefficients. Another thing that you can do here is look at the marginal effects, at the mean and the average marginal effects. You can quietly use the regression with y list and x1 list. This is exactly what we did above. And then you can use margins, comma, dy dx, star means calculated for all the variables, and you can use at means or not use at means, and that would give you the average marginal effects. So if you see at the output, these are the marginal effects at the mean and the average marginal effects. And we have for weight is minus 5.53, and here's 5.53. So one thing you can see from here is that these marginal effects are exactly the same as the coefficients. Everything is the same here. And that's why you can go ahead and you can interpret the magnitudes of these coefficients. We will see later on that when we go to the probit and logit models, this is no longer the case. You cannot interpret the magnitudes of the coefficients, only of the marginal effects. But here in the OLS regression example, you have a case where the marginal effects are the coefficients, and that's why you never have to calculate these marginal effects for your actual program. Okay, well, so far we talked about how to do a simple regression using just one independent variable, and now I will talk about how to do multiple regression using several independent variables. In this case, I will do a regression of y list and x list. Notice that I don't have the one here just for one independent variable. I have all three of them linked. And this is the output that I have for that. And we can see this coefficient that was minus 5.53 before, now it's minus 7.12. It changed a little bit when we put these two additional independent variables, and that's normal. So the way to interpret this coefficient is that if the weight increases by 1 unit, which is measured in 1,000 pounds, you will have a minus 7.12 decrease in miles per gallon for the dependent variable. And now you need to look whether or not the coefficient is significant. So these are the standard errors. The t-statistic would be equal to the coefficient divided by the standard error. And we see if this one is outside the critical in the critical area, which is typically between minus 2 and 2, approximately. And this is the p-value of the t-statistic being in the rejection region, which is less than 0.05. Likewise, the confidence interval does not contain 0 in it. So this, and these indicates that we have a significantly different from 0 coefficient. Okay, so we have a statistically negative significant relationship here. For the price and foreign, notice that this p-value is larger than 0.05, so we have results that are not significant. So I will not interpret those magnitudes because although they are positive or negative, they're not significantly different than 0. So for all practical purposes, they are like 0. There's a lot of noise there. And the way to interpret this in ANOVA table is the same as above. These are the sum of squares for the model, residual, and total variation. And these are the degrees of freedom. Notice that now we have 3 independent variables. And this divided by this is this divided by this is this. These two divided would be an F statistic of 15. And the p-value for this F statistic is less than 0.05. Therefore, we reject the null hypothesis and we have results that are jointly significantly different than 0 coefficients. The R squared is calculated as the sum of squares for the model divided by the total sum of squares. That's 0.67. So 67% of the variation we can explain with the independent variables, and the rest is due to error. The adjusted R square is lower as we included more variables in here. Okay. Unfortunately, when you have more independent variables, you can no longer plot things, because it was easy before to do a scatter plot of x and y. Now we have several x's, so we're not going to plot things. But we can still calculate the predicted values for the dependent variable using predict. I'm going to call this y hat, comma x beta calls the predicted values, and we can summarize the actual values and the predicted values. And when we summarize this, again, we see very similar results. Likewise, you can calculate regression residuals by using predict E hat, comma, residuals. So this is the option that I'm calling, and this is the name I gave it, and then I can summarize E hat. And again, you see those, the mean is very, very close to 0. That's a good thing. If you look at the data, these are the Y hats and E hats that we estimated and we put in the data. And here again, this one was calculated by using the intercept plus this coefficient times the value of weight 1, which is this one, plus this coefficient here that we have times the value of this price right here, plus this coefficient times the value of this price here. That's how we got Y hat. And E hat is the difference between this Y, miles per gallon, and Y hat. That's the residual here. And likewise, all of these Y hats are if you plug in these coefficients with the actual values of the independent variables to calculate the predicted value. So you can see some of these predicted values. Look at the residuals. Again, some of these are not predicted as good as we want them to be. But on average, we have a pretty good regression as indicated by high R-square and significant coefficients. The next thing that you can do is do a hypothesis testing for joint significance of coefficients, and you do this by using test and XList. So here we have the coefficient on weight 1 equals 0, on price equals 0, and foreign equals 0. So null hypothesis is that they're all not significantly different than 0, and the alternative is that at least one is significantly different than 0. And as you can see, this is the F statistic exactly from the ANOVA table that we talked about before. So again, we have a p-value less than 0.05, and we have joint significance here. Okay, the final thing to do here is marginal effects. And you do this by using margin, comma, dy dx. Star means for all the independent variables, at means, and the average marginal effects. And what at means, or the average marginal effects, means that first of all, we calculate, if it's at means, you calculate the mean for the first independent variable, for the second, for the third, and then you calculate those marginal effects for this average using these mean values. And here you calculate the marginal effect for every person, and then you average those out. So again, these are the marginal effects here, and you can see in the OLS or regression model, we have they're exactly the same as the coefficients. So in this case, you can just go ahead and interpret the coefficients, and there's no need to use the marginal effects, but that won't be the case for future models. I think this is all I had for how to do linear regression in Stata. Thank you for watching, and please watch more videos.